Okay, hey everyone, thanks for joining for our webinar today. We're just about to get started. Everything is up and running smoothly now. So just a brief introduction. If you look on your screen, there is a Q&A tab that you could access and submit any questions you may have that we will try to address at the end of the presentation. But I'm going to hand things over to Steve Nigro shortly. He's here from Regenesis. He's going to talk about some of their new remedial technologies. Steve.
Thanks, Jordan. Thanks, everybody, for jumping on the call here this afternoon. Also for the folks physically here at the DOH. My name is Steve Nigro. I'm the Pacific District Manager with Regenesis. I've been on board for 2 years now. Some of you may have worked with Jack Peabody in the past. He retired with us in June of 2013. After 18 successful years with the company. My background, real quick, is with about 17 years with a remedial construction contractor called NTAC, where we did a lot of soil stabilization, large-scale excavation, shoring. I also have Kelly Smith. She is the Director of Landscience Technologies. That is Regenesis's Vapor Intrusion Mitigation Division. So this afternoon, I'm going to be, we're going to split the presentation in half, and I'm going to be touching on a new accelerated bioremediation technology called Plume Stop. And then I'm going to hand it over to Kelly Smith, who's going to touch on our new technologies for vapor intrusion mitigation. Before I do that, though, for some of you that may not be familiar with Regenesis, we're an integrated site remediation company. So for the past 20 plus years, we've developed technologies to address soil, groundwater, and vapor intrusion. So our corporate headquarters is in San Clemente, California. We've got a very robust R&D department that makes advancements on some of these existing technologies, and then also development of new technologies. Then we have technical engineers. These are folks that have been doing these type of integrated solutions for 20 plus years. We average about 150 proposals a month at Regenesis. So we're looking at a variety of different constituents of concern. We see a lot of different soil types, different site scenarios. So we've got a pretty stout database and institutional knowledge looking at these remediation projects. Jordan, if you could just go ahead and...
Here. There you go.
Yeah, so real quick, what we're doing at Regenesis, fundamentally this graph shows, we're addressing vadose zone soil contamination as well as groundwater remediation. So underground storage tank, contamination leaking into the, migrating into the soil and then into the groundwater. So fundamentally, some of the things that you may be looking at a daily basis, we are providing technologies, whether it be chemical oxidation to address a source area for mass reduction, followed by a polishing step with bioremediation. And then, of course, the vapor intrusion mitigation. Next slide. So real quick snapshot, we got started with our ORC advanced compound going back again 20 years ago. This is where we are today as a company. So enhanced bioremediation for both petroleum hydrocarbons and chlorinated solvents. We've got a pretty good arsenal of technologies. We also have our own bioaugmentation, ISCR, chemical reduction. We have our own mobile iron that we use in conjunction with our high volume donor for anaerobic bioremediation, chemical oxidation, enhanced absorption. The one I'm going to be touching on today is the accelerated bioremediation. And then one really a big milestone for us as a company is we are now self-performing our own injection and overseeing soil mixing work. Next slide. Doing this for 20 years, we're looking at some of the challenges. A lot of fairly mature industry, a lot of the sites that are left are pretty complex sites. So go ahead and hit slide. You can keep going, just keep hitting it. So what we saw is, issues related to matrix back diffusion, rebound. the migration of these plumes, the overall risk associated with the plumes. And then, with bioremediation for groundwater, it takes time. So we developed, you can go ahead and hit it. So we developed what's called Plume Stop. So this is about 4 years of homework. And what I mean by homework is from the bench scale standpoint, and then also a very robust beta test program. Plume Stop is liquid activated carbon with polymers and nutrients. So it is, the features of the technology is rapid reduction of groundwater concentrations within days to weeks after injection. You can go ahead and hit the next slide. This enables for these lower concentration tailing plumes, and this could be for both chlorinated solvents or dissolved phase petroleum hydrocarbons, a way to meet stringent criteria for groundwater targets. The principal patent for the technology, so the main, I would say, feature would be the wide area distribution. So this is colloidal activated carbon. It's about the size of bacteria. It's 1 micron in size. It enables us to widely distribute Plume Stop within the formation. Go ahead and hit the next slide. This also serves as far as the liquid activated carbon. It's going to stay in the formation for years to decades, and it provides a means for ongoing treatment, and I'll touch on that in a little bit. So, activated carbon's been used in the industry for years from an ex-situ application standpoint. Within the last 10 years, there's been applicators out there, technology firms, that have fracked in larger particle size carbon in the formation. And what we've seen in, through the EPA and specific states like Colorado and Kentucky, these technologies have been fracked in near a monitoring well. And the problem is that when you're talking about 40 or 50 micron sized carbon particles, those are not penetrating the pore throats, the soil pore throats. So you're getting limited radius of influence. And as you can see there from this diagram, there's also within that treatment interval a lot of contamination that's missed. But you can go ahead and hit the next slide. What's happening here is that they're setting up an injection point near a monitoring well. They're fracking in this larger particle-sized technology, and they're flooding the well with carbon and saying that the well is clean. You can go ahead and hit that. So basically, that is something we wanted to stay away from. So the other part of this is to show the biodegradation. So regulators are asking, hey, great, you're absorbing contamination on the carbon. Where does the contamination go? That's another point that I'm going to touch on in a bit. You can go ahead and yeah. Thank you. So again, what is Plume Stop? It's colloidal activated carbon, size of a bacteria. It's got huge surface area for extremely fast sorption, and it's used in support of biodegradation. You can go ahead and do that. This is a scanning micrograph shot of a sand particle. I think it's a great illustration. So you're at a site, you're trying to treat the groundwater. You're going to inject Plume Stop via direct push or an existing well network into this formation. Here's fundamentally what it's going to look like. You can go ahead and hit the next slide. Plume Stop is going to leave a thin coating over the sand particle. And this is the biomatrix that I'm referring to. So this is the platform where the contamination is going to get absorbed onto, and with the microbes promote the biodegradation. The other feature of this, when we're talking about matrix back diffusion or rebound, so let's say you've got slowly diffusing contamination, which causing these lower concentrations, difficulty to close sites. Once the contamination is biodegraded on the platform, if you will, that carbon platform, it creates more surface area for additional biodegradation, for additional sorption and biodegradation. So one of the bench scale, go ahead and hit, one of the bench scale tests we did is for the distribution aspects. And so this is a column study. It was done with 2-inch by 2-foot columns. There were 3 tap water floors. It was gravity fed. It was a 48% coarse sand with 11% finer grain material. And we tested plume stop, the liquid activated carbon versus the powder activated carbon. Go ahead and hit. As I mentioned, it was gravity fed. Next slide. So to the left is plume stop, to the right is the powder activated carbon. Go ahead. As you can see, after pour one, you're getting a thin coating of the plume stop through the column where the powder activated carbon is not moving. Next slide. And then by the third tap pour, you're getting complete distribution of the plume stop through the sand column. We recently, and this is a new technology for us. We introduced it at Patel last year after an extensive beta test program. We're now full commercial with it, but it's an evolving technology, and we're continuing to do bench scale and field tests. Hey, can we sorb more contamination on this platform? Or let's look at another way. Like, for example, we just did a 16-foot column test with the plume stop. You can go ahead and, but the point there is that, you're not going to get the radius of influence with the larger particle size. As I mentioned, a beta test program. We did one with the Central Coast. This was a proof of concept test for plume stop at several former dry cleaning sites. So in this particular beta test program, we were dealing with CVOCs. Go ahead. So dune sand formation, the water table was at 13 feet with annual groundwater flow at 30 feet a year. We had very high redox conditions and no attenuation was evident. Next slide. PCE concentrations were 550 ppb. Again, no daughter products present. So we did a combination of plume stop, the liquid activated carbon, with our high volume donor. So a lot of the designs that we're doing these days, if we're seeing that the redox conditions are not amenable, we're gonna go ahead and add a high volume donor up gradient of our plume stop injection points. Then we also added the BDI. So here's a shot of what the proof of concept. This is not a typical design for plume stop. Again, we were trying to show, the goal here was to show treatment of a specific monitoring well with these tailoring concentrations. Next slide. That shows the groundwater flow. So there was 12 points total. Next slide. With, again, the combination of the HRC, the BDI plus, and the plume stop. Next slide. So 32 pounds of the plume stop. Our treatment interval was 8 to 25 feet below ground surface. And we also added, to help further bio-augmentate the BDI plus. This shows the historic data of the chlorinated solvents. As you can see, next slide. Steady increases in PCE with no daughter products. We had aerobic conditions. This is just another graph showing groundwater concentrations prior to the plume stop injection. Go ahead. Next slide. So this is an interesting slide. When we're talking about the biodegradation component, as I mentioned before, sorption is a key element, so you're going to get that rapid reduction. But the tests we're doing now, and this includes biotraps, we're looking at microbial activity. And the premise here, and you can go to the next slide. So the application of plume stop, you're seeing a rapid drop in groundwater contamination. Next slide. We're establishing the redox conditions that we need for the anaerobic conditions, making sure that we've got a condition where these bugs are going to thrive. So we've got no competing terminal electron acceptors. We're seeing a decline in that. Okay, you can keep going. Now, on the left, this box on the left here shows a suite of microflora that we tested post plume stop injection going out 90 days. And the fundamental point that we're trying to make is this. If the microbes are getting in touch with the contamination on this biomatrix, they are doing their job. You can go and hit the next slide. So there's your application. Next slide. We see immediate drop in groundwater contamination. Next slide. Then we're seeing, around the 50 to 60 day mark, a significant increase in microbial activity. Next slide. So you can see the percentages there in the different microflora that's breaking down the contamination. Next slide. And then a drop in microbial activity. So basically, the microbes are doing their work. They're consuming the contamination. As the contamination is biodegraded, we're seeing that steady decrease in contamination. Next slide. So the study found, based on this beta test, we had greater than 99% reduction of PCE concentrations within 14 days. We established optimal redux conditions. And then again, we were monitoring post-inoculation trends. Another interesting feature, which may be of interest on the vapor intrusion mitigation front, is based on the success at these former dry cleaning sites. We are now in a pilot test in regards to a dry cleaning site where they had done a competing bioremediation approach, and they have a stall at vinyl chloride. The adjacent residential properties had high readings for vapor intrusion for vinyl chloride. We are actually using plume stop in this pilot test to sorb and treat the vinyl chloride, thereby reducing a potential pathway for the VC. So I will be forwarding some additional case studies for anybody that's interested on that front. Next slide. The other key component of this is, we've talked with a lot of clients and regulators about, okay, plume stop, we don't have 10 years of data, but 9, 12 months out, we're seeing continued non-detect for PCE and related daughter products. So it is not only absorbing the PCE, but also their daughter products. Next slide. So the conclusions are, again, lines of evidence for post-degradation, and all data was taken from groundwater samples alone. Next slide. So really, I have another case study on a solvent site, but it's fairly redundant. For the sake of time, I'm just going to summarize. We offer free design services. So for any sites where the key take-home message for plume stop is an accelerated biotechnology, it's for dissolved phase plumes. Our preferred guidelines are we don't really want to look at anything 10 parts per million and above concentration-wise, and this is respectively for both the chlorinated solvents and the petroleum hydrocarbons. We are looking at new formations, and we will not be shy at looking at higher concentration levels. But that's really one area right now where there's a certain capacity on the isotherm testing that we did bench scale-wise of how much that carbon can hold. So that's something that we take into consideration. We also add either our high volume donor or the ORC Advanced if we're dealing with the petroleum hydrocarbons. So it's not meant for source areas. We're going to recommend maybe a combination of ISCO coupled with a plume stop barrier down gradient. But a really unique new technology. If anybody, whether it be on the room or through the webinar, has any questions, technical questions, I have a white paper. I can send some things digitally as far as these case studies, along with some additional bench scale stuff that we've recently done. But anyway, I live and work in Pleasanton, California. My contact information, want to thank Jordan and Roger for letting me share this new groundwater technology. And I'm going to transfer it over to Kelly Smith with Landscience Technology. Thank you.
Hey, thanks, Steve. So as we move over to Kelly here, let's take any questions that we may have from our audience.
Hey, Steve, what's the concentration of organic carbon you think you're putting in the
our yeah, the minimum one that we're using right now is right around 1,500, 1,000 to 1,500.
Steve, you raised a question that you said people had asked you. I didn't really hear what the answer to it was. But you're sorbing these contaminants, you're removing them from the groundwater.
Yeah.
What's happening to them? How do you know that they're being degraded?
Great question. And that's an ongoing step on our part. So there's two things that we're doing right now, since it's a fairly new technology, to show that biodegradation piece. One is, again, the microbial counts. So we're seeing that uptick in microbial activity, meaning that they are biodegrading let's say the chlorinated solvents, the PCE, followed by that decrease. And then the second part of that is we're actually going out now and taking post-sample cores and actually then sampling the mass reduction within the column, within the treatment area that we've done. And so, again, continued documented sites where we're trying to get now some post-sampling to show that bioremediation piece. And I'll be forwarding that to anybody that's interested. Does that help?
Yeah.
Okay.
My question, you're saying that about 10 parts per million concentration, you don't recommend using the activated carbon or this carbon?
We can. I mean, it's a fairly new technology, and I would say our comfort level initially was with that 10 ppm and below. And again, both for petroleum hydrocarbons and the chlorinates. We are now looking at higher concentrations.
Because if there's degradation occurring of the sorbent particles, then it could be free to reabsorb.
Right. Right.
Okay, thanks, Steve. I'm going to turn things over to Kelly now. Just hit answer.
Yeah, thank you. Thanks, everybody. My name is Kelly Smith. I'm with Landscience Technologies, which is a division of Regenesis. Regenesis started the Landscience Technologies division in 2007. Jordan, how do I advance?
Enter.
Too soon. No, enter.
Sorry about this.
Okay, thank you. Regenesis started the Landscience Technologies division in 2007 to develop solutions for vapor intrusion mitigation and brownfield redevelopment. They saw a nice synergy between the two divisions to be able to clean up the site and then take it to construction. So our flagship product is the Geo-Seal Vapor Intrusion Barrier, which is a sub-slab barrier for primarily new construction. The Vapor Vent is a low-profile trenchless venting system. And then the retro coat is a coating for existing buildings to address vapor intrusion. And that's our newest technology released in 2012. So the topics I'll go through various vapor intrusion mitigation options, vapor intrusion barrier options, and then I'll talk more about new construction with Geo-Seal and existing buildings with retro coat. So there's various, many mitigation options that are available. Some of the more common ones would be active venting or subslab depressurization, passive venting, and then barriers for vapor intrusion. So looking at active venting, in this instance, we're mechanically removing vapors. So we're putting in pipes, network of pipes, horizontally and through the roof, putting on a fan, and actively removing the vapors. With a vapor intrusion barrier, that can provide maximum protection because you're creating that negative pressure underneath the building. It's also able to be verified, which is desirable. Some of the challenges with an active venting system over time include the long-term operation and maintenance associated with it, the risk of the system getting turned off, especially if that is your only protection and you're not including a barrier. Then if the system gets turned off or there's a failure, mechanical failure, it could be problematic. Also in some areas might have air permitting to consider, and also the engineering of the system. For a single family home, a small footprint, active venting might be very easy to install, but if you've got a large warehouse building, for instance, it can be difficult to engineer it correctly and get the radius of influence you're interested in. Passive venting systems, these equalize the pressure differential. These are a network, again, of pipes underneath the building, horizontally, and pipes going through the roof. But these don't have a fan. It's not mechanically removed. There's no blower. So it's a passive system. Once it's installed, it's working, equalizes the pressure differential, and there's no long-term operation and maintenance associated with it, which is why it's a desirable system. And the growing trend we see, or pretty common, is to design a system passively with the option to turn it active later if needed. Vapor intrusion barriers eliminate the vapor intrusion pathway by sealing off the underside of the slab. So we're sealing off any pathways into the building through cracks in the concrete or voids between the conduits in the concrete. So we're giving that concrete slab a good seal and sealing off any of those pathways. Some things to consider with vapor intrusion barriers are chemical resistance and constructability. I'll cover that more later. And oftentimes the vapor intrusion barrier is going to be used with a venting system, whether it's passive or active. So a common approach, especially for new construction, is installing a vapor intrusion barrier along with a venting system underneath it. So basically the vapor intrusion barrier is sealing off any pathways, and the venting system is giving the vapor an area to collect and to be removed from underside of the building. Some barriers that are considered for vapor intrusion, moisture barriers are one, HDPE, thick high-density polyethylene geomembranes, spray-applied systems, and then composite systems like the Geo-Seal, or coating systems like the RetroCoat. So I mentioned that there's important considerations for barrier selection. One is chemical resistance, so making sure that the barrier we're selecting is going to be chemically resistant against the contaminants we have on site. So if you've got chlorinated solvents, you would like a barrier that would be chemically resistant against chlorinated solvents. Constructability-wise, it should be sealed effectively, and it should be easy enough to install. It's not too cost prohibitive. We don't want something that's going to be susceptible to construction damage. So all those things to consider with constructability. Cost-wise, it's got to be cost-effective enough to not be prohibitive against the project. Also, warranty is important, making sure it's going to be warranted for VOCs and vapor and not just for moisture. Also, quality control, making sure that we are able to verify the integrity of the system. So first, starting off with moisture barriers. These are thin mill plastic sheets. These come from the waterproofing industry. So when a general contractor says vapor barrier, a lot of times they're referring to a moisture vapor barrier. So it's very important to differentiate. If you've got chemical VOCs, chemical vapor, it's not appropriate to use a moisture barrier to try to prevent the vapor from coming in. So these are 10 to 15 mil sheets. They're taped together. I have a sample I'll pass around. So also the quality of the installation, over time these systems can become unadhered. The tape can break down the adhesive of the tape, resulting in a system that's not vapor tight. They can also be susceptible to rebar, to construction damage from rebar or construction traffic. They're not warranted for vapor, they're meant for moisture. They're not recommended by the EPA for vapor intrusion. In 2008, the EPA released this Mitigation Primer recommending a minimum thickness of 30 mil because of that susceptibility to construction damage. So various regulatory agencies around the country in their guidance documents also recommend between 40 and 60 mil. That's basically the industry standard for these types of systems. High-density polyethylene geomembranes is another option out there. These are very chemically resistant, very thick, robust sheets. They're common in landfill applications and methane mitigation. So for a large flat site, an HDPE geomembrane 16 mils thick is a good option, because you're just going to roll out that sheet and weld those seams together. Where it can be prohibitive is if you've got a building you're trying to construct and you've got foundations to seal around, conduits, electrical plumbing. That system can be very labor intensive because they have to batten into concrete, use batten bars, weld the sheets together, weld around penetrations. So all that mechanical attachments can be labor intensive. Spray applied asphalt latex membranes, these solve the constructability of HDPE. So these are very simple to install. You lay out the geotextile fabric, spray apply asphalt latex, and then put another geotextile on top. So for methane mitigation, it's an appropriate product, and it can be easily installed and sealed. The limitation with asphalt latex as your protection is if you've got a site with chlorinated solvents or petroleum. Over time, those chemicals can absorb into asphalt latex and can break it down. Which is what brought us really to the Geo-Seal system. So we saw this need in the marketplace for technologies specifically to address VOC contamination, not just methane, not just waterproofing. So we developed the Geo-Seal system, which is a combination of a spray-applied asphalt latex with 2 layers of high-density polyethylene. So you take that chemical resistance of HDPE and we combine it with the spray to make something that's going to be chemically resistant but also easy to install. The RetroCoat system, we saw another need for user-friendly products to address vapor intrusion into existing buildings. So we developed the RetroCoat system, which is a coating that can be used in existing buildings on top of the existing concrete slab. It can be used as a finished wearing surface, and it's designed specifically and tested for VOCs, vapor intrusion. So starting off with Geo-Seal, looking at new construction, we oftentimes start with a venting system. So this is a picture of the vapor vent, which is a low-profile trenchless venting system. The vapor vent is used in lieu of a traditional pipe and gravel system. What's nice about this is it just needs about 2 inches of gravel or some sort of permeable subgrade to be embedded in, whereas a PVC pipe, you're typically going to dig a trench 12 inches and fill that whole thing with gravel. So we're reducing the gravel and we're reducing that trenching involved. So the vapor vent gets laid out. You know, a typical layout might be 50 feet on center, for instance. So it's just laid out in a grid-like fashion. We connect the vapor vent to a pipe that would go through the roof, or to pipes that go through the footings by connecting it to a pipe with the adapter pieces. And this is a detail showing the vapor vent being connected to the vent riser. So basically, the vapors come up, find their way to the vapor vent, and can find their way to the vent riser and be released outside of the building. Next, we're going to install the Geo-Seal base. So this is a layer of high-density polyethylene thermally bonded to geotextile. This gives us our first line of, our main line of vapor defense. So we roll out the base layer. We're going to seam those sheets together by overlapping them 6 inches and spraying in between that overlap. Then we're going to spray the core on top of the whole. Yes, that's it. Steve will pass around a sample of the base. So the plastic part, that's the HDPE, and then the fuzzy side is the geotextile side. So the HDPE gives us chemical resistance. The geotextile gives the system a little bit more strength and prevents it from slipping and sliding on the subgrade. Next, we spray apply our core layer to 60 mils. This is an asphalt latex emulsion. It's got no VOCs. It's a water-based product. And we use the core layer really as a sealing mechanism for the system. So we're using it to seal around penetrations and seal the system to the concrete and foundations. Sealing around penetrations, you know, for any type of barrier you would be using, sealing around penetrations, making sure it's vapor tight, sealing to the foundations is very important. So for us, sealing around penetrations, we're going to use a combination of our HDPE layer, our core, a reinforcement fabric, and then a cable tie. So we're getting a really good seal around those penetrations. We're also terminating to the perimeter. So we do that by spraying 6 inches onto the concrete and basically bringing in all 3 layers, then spraying a final termination seal. So again, just showing that importance of sealing the barrier around the perimeter. After we install the base, spray the core, we'll do our QA/QC, which I'll talk about. And then after that's done, then we apply the bond layer. So the bond layer is the 3rd layer of the Geo-Seal system. It's another layer of high-density polyethylene thermally bonded to geotextile. We roll the bond layer perpendicularly to the way we rolled out the base layer, so there's no testable seams in the membrane. The bond layer we're going to seal together by overlapping at 6 inches, spraying along the overlap, and then we're going to set the rebar on top, and then pour the concrete directly on top of it. The bond layer also allows the system to adhere to the underside of the slab because it's got that geotextile, so it'll create a mechanical bond with the concrete. So if you've got a site with settlement, you'll still have an adhered system to the bottom of the slab. The Geo-Seal system can be used in waterproofing applications, so we'll do sometimes applications, below grade applications, where there's waterproofing and VOC vapor involved. Showing chemical resistance of the Geo-Seal composite system versus just a spray applied asphalt latex with geotextile below and above. We've conducted various extensive testing on it in the presence of PCE, TCE, and benzene contaminants to show that difference. So with the Geo-Seal system, we're showing 685 times lower diffusivity. Permeation, we're showing that it's 18 times less permeable to VOCs, to PCEs specifically. Weight gain, we're showing that it's 5 times more resistant to weight gain. The permeation refers to, how much is absorbing into it, desorbing off of it, and going through it. So we're showing 18 times less. Weight gain is simply saying how much is absorbing into the two membranes. The Geo-Seal system absorbs 5 times less than a spray-applied asphalt latex. So quality control, there's various ways that we ensure the integrity of the membrane and installation. For one, we work with a certified applicator network. So we've got applicators around the country that can install the system that are certified by us for installations. We provide free online inspector training and certification. So oftentimes for most of our projects, there will be a third-party inspector overseeing the QA/QC process. We do thickness verification where we take coupon samples and test the thickness with the caliper. We also employ smoke testing, which I'll show, and we do visual inspections. So smoke testing is something that applicators would administer and the inspector would oversee. We pump smoke underneath the membrane and look for any voids in the system, so any areas where smoke's coming out, and we'll repair those areas and then run the smoke test again until we have no more smoke. It's a great visual verification that the membrane is free of any voids and pinholes. So this is the completed smoke test where you have no more smoke coming out except through the vent riser. We offer design assistance to the consultants we work with. So we've got an AutoCAD library. We can customize the CAD drawings. We can do plan reviews. Warranty options. So the Geo-Seal system is warranted specifically for VOCs. We have a material warranty offering, and we also have a system warranty offering. And the system warranty covers material and applicator workmanship. So this is a project we did locally here in Honolulu. This is luxury condos, the luxury auto center. The Geo-Seal system was used for vapor intrusion and for waterproofing as well. Steve, is this a picture you took?
It is.
Steve Nigro here took this beautiful shot for us. So it was used for combination. We also used ORC Advanced on this site. So there's a lot of complications or just a lot of challenges with this site with the chemical contamination and also the waterproofing. So we ended up customizing a system for this. Here we're showing our Film 11 being rolled out with the Geo-Seal core being sprayed on. We had piles to contend with. We had a thick mat slab. Here's the Geo-Seal core sprayed out. And here's a shot of them running the smoke test. So that smoke machine blower is blowing the smoke underneath where they're walking around looking for any pinholes. And then once the smoke test is completed, then we roll out the bond layer on top. So some other projects around the country, a school up in Oakland. This is under DTSC oversight. This was close to an old auto repair shop. A maintenance facility in Dallas. This was preemptively used there. Residential in Raleigh, Connecticut, Raleigh, North Carolina, that had vapor intrusion and waterproofing. This bank in Dallas, you can see a post-tension slab application, so using it around various foundations. So now I'll move into existing structures. So looking at existing structures, the types of projects we're seeing are historic structures where they want to keep the historic facade, strip mall dry cleaner sites, buildings that are being converted to something else, perhaps office buildings. So the mitigation options for existing buildings, one is using a vapor intrusion barrier. So you could, for instance, use the Geo-Seal, either in a crawl space or in an existing building where if they're removing the slab, you could put down a barrier and then pour new concrete. Or if you have high enough ceilings, you could install the barrier on the existing slab and then pour concrete on top. You know, with most vapor intrusion barriers, in addition to Geo-Seal, it's going to require concrete protection. Another option available is sub-slab pressurization, active venting. And now we've developed the vapor intrusion coating. So this is a coating that can go down on existing concrete and doesn't require a topping slab of concrete. So you don't have those clearance issues that you might have had otherwise. So in the development of the retrocoat system, we evaluated over 1,000 different combinations of resins and hardeners, and we were looking at chemical resistance, durability, and also VOC content. So we developed the RetroCoat system. It's designed and tested specifically for PCE benzene. Has no VOCs in the technology, and it can be used as a wearing surface. It doesn't require any concrete on top of it. And it can, in fact, even take forklift traffic. It's a very durable system. So the testing method we used, we developed this testing method to really demonstrate the performance of the membrane. So we've got, in the test barrier, we've got the RetroCoat, and then we've got contaminated water below. And then we're testing what's coming through. So we're basically simulating a vapor intrusion condition. So we ran this test over 5 months. We started at 500 ppmv and then brought it down to 25 ppmv. So we start at high concentration, go to low concentration. And we're testing it at steady state permeation. So once we have an amount coming through the barrier for 3 months or for 3 weeks that was steady, we consider that the steady state permeation. So from that, we were able to develop diffusion rates for the RetroCoat, and basically it demonstrates that the RetroCoat will provide 4.5 order magnitude reduction of the contaminants. So the application process for RetroCoat, we start with surface preparation, and our certified applicators would handle this. So we start with surface preparation, we repair the cracks, seal the penetrations, apply 6 mils of the primer, and then apply 20 mils of the RetroCoat. We also recommend moisture testing for the system. So starting off with surface preparation, we'll shot blast the concrete to give it a profile. Then we'll make repairs as needed. So we've got different ancillary products that can make those repairs. We seal around penetrations by sealing it with a bead of caulk. We've got a gel that will repair some of the cracks in the concrete. Then we put down 6 mils of the primer. And the primer prevents some moisture from coming through and also gives better adhesion of the RetroCoat to the concrete. We have a red tinted primer available, so if we're concerned about wear of the surface in a particular application, we could put down a different color primer so that if they wear through the RetroCoat, they would see that color and that would prompt a recoat. Next, we're going to install 20 mils of the RetroCoat. So it's 100% solids. We install it with the notch squeegee to ensure that thickness that we're going to get. Then we're going to back roll it. So we've got various colors and finishes available. We can customize these. Some projects that we've installed RetroCoat, so manufacturing facility, where we combined it with passive subslab or passive venting. This had forklift traffic. This is a high-tech project in the Bay Area over a solvent plume, 2-tone custom color finish. This is a housing development in New York. So we went in the basements. There's a high groundwater table, it's a former MGP site. We went in the basements of those of that residential, that huge block right there. And that's it.
Okay, thank you, Kelly.
Sure.
Let's open it up for any questions from our audience or people on the webinar.
What's the cost of the RetroCoat per square foot wild range?
The cost, I can tell you on the mainland, it's $4 to $6 per square foot generally. So
Right.
it would probably be in the same range here because it'd probably be in the same range, judging on the Geo-Seal cost over here as well.
How about what's the Geo-Seal cost without venting?
Without venting, probably it's probably between $275 to $375 per square foot. And on the
How would the venting included?
venting adds, between 10 to 25 cents per square foot. Venting is kind of a nominal cost. And the Geo-Seal pricing, so that is material, labor, and QA/QC. For the RetroCoat pricing, that includes surface preparation, material, and labor.
I have a question in terms of the warranty of the product.
Mm-hmm.
So I guess what's the general warranty on subsurface barriers?
We have, for the Geo-Seal system, we have various, we have a range of warranty options available. So material warrants that the material is free of defects, and we have the ability to go up to a 30-year material warranty. Warranties are given on a job-by-job basis, and there's a list of things we're going to want to see, like soil and groundwater report, review the design. For certain warranties, we'd want to see an inspector out on site. So there's a list of things. And also for Geo-Seal, we have the ability to give a system warranty, which covers material and applicator workmanship. And we can do that up to 20 years. And then on the retro code, it's a little bit different because that's more in the range of like a 1 to 5 year warranty. And it's more against delamination. It's just a little bit different because it really depends on the activities taking place inside the building. It's more variable.
Let's see.
How about one issue that came up here especially on the Symphony site, is the whole venting.
Right.
And, the idea is to keep this stuff out of indoor air. So some of the vents I've seen on the mainland, they run them up to the ceiling, up to the roof line, and the HVAC system is sitting right there. So what kind of discussions have you heard on the mainland about the advantages of venting versus just putting in a barrier and leaving it at that without venting? When would you put in venting?
Passive venting is put in pretty often. So 92% of our projects include venting, and it's typically going to be a passive system. Maybe a passive with the option to turn it active later if needed. But with our vapor vent, for instance, it's such an incremental cost that it's a lot easier to install it from the start and have the ability to put a fan on later if you really wanted to, or you have other options if you have a venting system already in place.
I was thinking even passive venting.
Yes.
Have you heard any other states or even anyone in EPA expressing any concern about venting, period, just because of the chance that the vapors coming out of the vents could get pulled into the HVAC system of the building?
I mean, it should be far enough from the HVAC system that that's not going to happen. So like the city of LA has a very strict methane mitigation code, and they really outline, how far the vent riser needs to be from inlets, doors, windows, HVAC systems. So people ask questions, we oftentimes point them to that as a rough guideline.
Okay. It's useful to know.
Yeah.
What do you do about future modifications, repairs? Somebody has a need to go and saw through the concrete to do some additional work. How do you handle that?
It's all on a case-by-case basis. So we need to know about it, and we'll have to send our applicator out to repair it. So we can make repairs. In fact, we have a project right now where there's a lot of conduits that were off, and they're moving all the conduits. We had to go back and make all those repairs. So if we know about it, we're able to do it. And it really depends on the specific type of repair. That's why it's difficult to say like a blanket. So it's difficult to give a blanket repair procedure, but in general, we're repairing the 3 layers that we've punctured. And if there's a new conduit, we're doing the penetration detail and adhering the new Geo-Seal to the existing Geo-Seal that's already there. So we can do repairs both on Geo-Seal and the retrofit side.
Okay. One other question I have is whether the presence or absence of a passive or active venting system, I guess, how does that affect the effectiveness of the vapor barrier? I'm sure you folks have studied that.
So for most of the sites, if there's very high concentrations, then we might especially want to see a venting system. But in general, it's like a belt and suspenders. So you've got the barrier, which is your main defense, but you're also incorporating a venting system just to remove the vapor from underneath the slab, just to give you a little bit more extra protection. Mm-hmm. But you don't need the venting system for the Geo-Seal to work. Geo-Seal will work without it. So we don't require the venting system. We're saying routinely it's used because it's a prudent approach to use that belt and suspenders approach.
But at the Symphony project, what is the final cost per square foot on the ceiling, including the testing?
The testing, I'm not sure. I think the installed cost of that was between $300 and $350 per square foot. Yes. For the Geo-Seal, But that's the main barrier area where we were doing, where we were using it for vapor intrusion. In the elevator pits where we were doing waterproofing, that was a higher cost because we incorporated a lot more layers. There was actually free product and water, hydrostatic head pressure. So that square foot range was higher order of magnitude. But as a good general, slab on grade vapor intrusion barrier cost, for that it was in the 20 to 50 range.
So there's also a venting system under there also.
Yes, incorporated venting. I think they ended up incorporated venting.
They did. So it's just a barrier.
We went back and forth on that, but I thought that
Well,
we
sounds
ended
like
up.
the venting is maybe just do the vents or outlet. Install it.
Yeah, seems like it.
And she said it was only its nominal cost. So,
Yeah.
10 cents.
Like 10 to 25 cents. It depends on the system too. If it's the vapor vent, it's going to be a lot less. If it's a PVC pipe venting, it's going to be a lot more than that. PVC pipe is more labor intensive and costly.
Okay, any other questions we have here or for our audience on the webinar? It doesn't look like it. Well, once again, thank you to Steve and Kelly for coming down here, taking some time to present to us. For now, this is going to conclude our webinar. If anyone has any questions, you could send me an email. It's available on the bottom of the screen, and we'll also be posting the slides and a recording of this presentation on our webinar page, which you can also see here. Thanks again, and we have no planned future webinars at this point, so if you have any topics you may be interested in or a presentation you may be interested in presenting, feel free to contact us as well. But thank you again, and hope to hear back from you with any comments or questions you may have. Thank you.